Hello, everybody. My name is Leah. I'm the administrative assistant here at Africa Fire Mission. I just want to welcome you all here today and thank you all for joining us today. We have a really great training today, Intro to Fire Dynamics. So I'm really excited that everyone is going to be here and able to join and attend it. It'll be a good one. So I'm glad you're not missing it. I just want to remind everybody that this training is recorded, and so I'm going to be posting this video on YouTube later on if you want to go back and watch it, if you want to review, or we also have our whole stock of old videos there too. If you ever are curious of what we've taught in the past or want to go refresh on something else, you're always more than welcome to look at those videos and also share those videos with your friends, as well as the link that you got here today, that registration link that you used to join. You're welcome to send that to your other pals in the fire service or anyone in the community that's just interested in the fire service. You can always invite them as well. And I will be sending out certificates today as well. If you join and stay for 70% of the training, that usually looks like 45 minutes. If it's a 1-hour training, it'll be 45 minutes. So if you stay for that whole time, then you're going to be getting a certificate with your name on it. And so I know I remind you guys of this every single time, but the name that is on your Zoom right now is the name that will be on your certificate. So if you have a funky name that sometimes it shows up as your wireless provider or your phone, and you do not want that on your certificate, please just change it. Or you can chat me right now and I can take note of it, but it's easiest if you just change it yourself and then it'll be done and the certificate will be correct. So please, if you can, do that. But I'm going to pass it off right now to Jose, and Jose is our fire safety advocate, and he has a word of encouragement for you guys.
Thank you, Leah, and hello, Africa. Now, today, usually we are represented in the whole of Africa, from Zambia to Malawi to all parts. Yeah, and now even in the States. So karibuni sana, welcome, and I truly appreciate you. I'm just from a trip in Western Kenya. Western Kenya is quite a big place, and the main reason for me to go to Western Kenya was just to empower and encourage the firefighters. And I got to meet Homa Bay County, which was part of us. I mean, part of the firefighters, but they've never known who Africa Fire Mission is. And that's actually where we are. My encouragement of the day goes, in the sense that when you have good news or good tidings your way on the fire service, it is always good that you get to share with your other fellow brothers and sisters in the fire service. If I'd say, don't keep that information on yourself, because somewhat you can imagine with me, when you keep everything in your stomach, finally you're going to constipate. better lack of a better word, So when you get it out, you get to actually have new thoughts and ideas come through your head. So I'm really glad that we have new kids on the block like Homa Bay and Kakamega County. Join us even in the Zoom and everywhere, and also are going to come in the symposium and learn more about it. So my encouragement of the day is, please make sure that you share any good news that you have with you, so that you can have more space to get more good knowledge in your mind. So back to you, Leah, and take us to the next stage.
Awesome. Thank you so much, Jose, for that. And before we start, I just want to remind everybody to please stay muted throughout the training. If you do have a question or just a comment, please raise your hand and we'll call on you, or you can type it in the chat. I monitor that throughout the whole training, so I'll be able to look. I'll say that for you. I can interrupt the session and everything. But if you can just please stay muted, that would be really helpful. But I'm just going to be passing it off now to Ed, and he's going to have an awesome training for us.
Great, thank you, Leah. Hi, I'm Ed Collet. I've been taught with Africa Fire Mission now since 2019 was my first trip to Kenya, and I've been teaching with AFM ever since. What we're going to be discussing today is fire dynamics. This presentation is taken from the UL Fire Research Institute. They have done a lot of work on different fire dynamics and how fire reacts and grows. So I took a train the trainer course on this at the Ohio Fire Academy, where I'm also an instructor. And it's got a lot of really good information for it. So I'll go ahead and start sharing my screen. There we go. Can everyone see it?
No, we cannot.
No.
Okay. Share. If I click the button at the bottom that says share, it works very much better. Okay.
There you go. We can see it now.
There you go.
Okay. So this was originally made by the head engineers at the Fire Research Institute. I've edited the content for AFM and what I think are purposes that we need for our Kenyan firefighters. We'll be covering how fire starts, how it grows, how it behaves, how it interacts with fuel, the building, and the environment. And the big thing of why we need to know about fire is we need to know our enemy and how it's going to work and how it's going to react. It's a natural phenomenon. Fire behaves based on laws of physics and nature and science. By understanding these, we will be able to better fight fire, put out fire, and have a better outcome for our communities and the people impacted by the fire when it started, because we will keep it to a minimum. So fires really, we need 4 things for fire to occur. We need fuel, then we need heat, and we need oxygen. And once those 3 things combine, it needs to keep a reaction going to keep flaming combustion. You know, fuel is all over. You know, the desk I'm at is fuel. Everything your house is built out pretty much is fuel, but it doesn't, we're not burning all the time. It's not on fire all the time. Well, it doesn't have the heat needed to release the chemical energy stored in it. So until we get heat, we can have as much fuel as we want, but we won't have fire. We can have fuel and we can have heat. If there's not enough oxygen, we won't have fire either. This is really important, and this is what's been driving a lot of the studies. Much of the fire today is what we call ventilation limited. It doesn't have enough oxygen to burn. It'll burn for a while, it'll consume all the oxygen available, and since you pulled that leg of the fire triangle or fire tetrahedron, you pull that leg out, the fire goes out. Until firefighters come along and open doors and open windows and give it oxygen, and then we get really rapid fire development. And that's one thing we need to really focus on. It used to be we'd come up and we'd just start breaking windows to get all the smoke out. Now, if we start doing that, breaking windows, opening all the doors, while we get the smoke out, we're letting all the air in. When all that air comes in, the fire grows. This makes it very important before we start opening up all windows and roofs and doors. We control everything till we get water ready to go on the fire. So as soon as we start the ventilation and that oxygen gets to the fire and it starts to flame back up, we can put it out right away. As opposed to just venting, letting all the smoke out, letting all the air in, and boom, the fire reignites, and now we have a larger fire than if we would have just went in before we opened and gave it the air it needed. And really the big thing is, if we take any one of these away, we're going to put the fire out. So if we take the fuel away, the biggest thing, we take away heat. How do we take away heat? Water is the firefighter's best friend. We use water all the time to put out fires as our main fire suppression agent. That takes away the heat, also seals the fuel away from the oxygen. When we use our fire extinguishers, like our dry chem, our ABCs, those are inhibiting the chemical reaction and also slightly displacing the oxygen when we're using our CO2 extinguishers. So we're breaking up this triangle or tetrahedron so the fire will cease, that it can't grow and it can't be self-sustained anymore. So here, unfortunately, I guess you can't hear the audio on this, but this is showing what fire is.
Oh, we can hear it right now, actually.
Oh, you can?
Yeah.
Fire is the result of fuel gases mixing with oxygen and heat in the correct proportion. Pyrolysis is a process when heat breaks down solids into fuel gases. Another word for fire is combustion, when the fuel gases mix with oxygen and are ignited by heat, which results in flames.
So the big thing, if you look at this, solids don't burn, liquids don't burn. The only thing that really burns and produces the flames that we see are gases, which is, if you look at this picture on the right-hand side, you can see this area of smoke. Well, that's actually off-gassing fuel. That's actually fuel from this sofa that it has become hot enough to actually off-gas, and it would be this off-gassing fuel that will actually burn. So the solid really isn't burning here. It's all of the gases that's being produced as it heats up. That's one thing we really, we need to remember, that if we cool that sofa down, and why we always want to keep things as cool as possible and use our water very efficiently, by keeping things cool, it doesn't produce the fuel to burn. If we put water on that sofa on the right side, it'll keep cool enough that it won't burn, and we'll also put out the fire on the left as we go as well. But it's all about keeping things cool. As we keep things cool, it can't produce the fuel. That's what's ultimately going to grow the fire. So some measurements involved in fire dynamics. We talk about temperature, energy, heat release rate, and heat flux. And these really become important to understand how the fire is going to impact a structure, a room, or the material that will start to burn. Temperatures really, we all know, we look at the weather every day and say, oh, it's 20 C today, or it's going to be 33 C out today. But what does that temperature really mean? It's a measurement of activity of the molecules that make up every material. I look at it, I kind of put it in perspective of when it's 0 C in Ohio here, as it often gets in the winter, I shiver. I move to generate heat. So the more movement there is within a material at the molecular level, the more temperature it has. So that's how to look. Temperature is based on the molecular movement of all the little molecules within the material. But here's really the important thing to look at when it comes to temperature. What's impacting us, especially as firefighters? So we look at 48 C is when our skin will start to receive first-degree burns. When we go all the way up to 72 degrees C, our bare skin is instantly destroyed. Now, to me, one of the most important temperatures to look at is the melting point of polycarbonate, which is 230 C. As firefighters, when we go in and we have our BAs on and we have the face piece is made out of polycarbonate. That is the weakest link in our protective ensemble that we wear. Notice our modern protective clothing that we have, our bunker gear, it doesn't even start to char till over 300 degrees C. Yet we'll melt our face piece off at 230 degrees C. It doesn't matter how good my bunker gear is. If my face piece fails, as soon as I take that first breath, I've already destroyed and severely damaged my respiratory tract if it's hot enough to melt my face piece. That's one thing we really have to be aware of, and maybe not get into situations where the room is getting too hot, and we always want to be proactive in cooling the rooms down with water to make sure that we don't get into elevated temperature situations where we can damage our face pieces. And the bigger thing that I look at, if we can keep a room cool, and as we go till we find the fire, if we're still keeping it cool and flowing water, that's helping the victims. The victims don't have our nice protective gear. You know, they might have cotton clothing on or bare skin. They're going to receive injury at 55 degrees C. So if we can keep the environment as cool as possible for them, we're helping to improve their survivability. So that's one thing with fire that we really want to look at, is trying to keep everything, even as we're going and we don't see fire, we want to make sure we're still cooling the environment with water. Now, energy, the heat is actually how much energy we need to apply to a material to increase the temperature. So if we add heat to it, the temperature goes up. If we take heat away, the temperature goes down. Temperature goes from high to low. So naturally, temperature will always go. If something's hot, it'll try to push out, and things that are cooler will get hotter as that heat energy flows from hot to cool. That's why we see things that aren't on fire now, eventually they can start on fire due to the fact that that heat energy is flowing from where it's hot to where it's cooler. Now, the heat release rate, this is a lot of, there's a lot of fire science involved in this, but the big thing with the heat release rate that we need to think about as firefighters at a basic level is how fast things are burning. So if something's burning, it's giving off energy either very quickly or very slowly. The slower it gives off energy, the more ability it has to have oxygen be coming into it and have the right amount of oxygen. If it gives a rapid burst of energy off, it can actually consume all the oxygen very quickly, and the fire basically goes out until more oxygen is introduced into the room. So as you can look in this animation, as something's on fire, you have your oxygen, and as the oxygen starts to go down, the heat release rate goes up, the oxygen goes down very quickly. And then when it gets to a certain level, the fire goes out. But we have high CO, and that CO, that carbon monoxide, is actually fuel. So as soon as it would get enough air available with oxygen, it would reignite. So you kind of just look at heat release rate compared to temperature is how much energy is being put out. So the flame of one candle would be 500 C, say roughly, and it's going to make 80 watts of energy. As a heat release rate, if you have 10 of those candles, the temperature is still the same, but you're producing more energy due to the fact there's more fuel being consumed and more energy being radiated. So this looks like what heat flux is. Look at heat flux. This is how much energy for a certain area of, area of material. So you can set a newspaper out in the sun all day and it won't burn, because that area, there's so much energy over a very large area. If we take a magnifying glass and concentrate that energy of the sun into one point, as we'll see, we add enough energy to a very small area that eventually we will get the paper to burn because of that concentrated energy. So the more energy, the more area the energy acts on, the slower that it raises the temperature. But if you concentrate that energy into a very small area, that will raise the temperature very quickly, and often that's where we'll see combustion. This is where we've actually changed a lot in the fire service, and has been a big impact, is the difference in our fuels. The fuels that we're fighting has changed over the years. It used to be, it was an organic fuel like wood, but still you have the new ones that, plastics, gasolines, those have changed. Woods, natural fibers, cotton, wool, those tend to burn cooler and a little slower. And then we went to the other side of the newer fuels, plastics, which, all types of plastics, polyurethane, polyethylenes, the foam in your sofas, all of that is basically liquid gasoline, because it's all a hydrocarbon. It will burn very rapidly, very hot, and it'll consume oxygen very quickly. Inorganic fuels that we look at, there's no carbon in it. So you're looking at magnesium, sodium, other metal fires. Most of these we'll see in industry and also today in automobiles with the newer metals that they're using, especially the magnesium that we'll see. And we have to fight the fire slightly different. Inorganic fires, we cannot really fight with water due to the different chemical reactions. Those need to be actually with chemical agents, or often just dirt to smother them to take away the air side of the fire tetrahedron. While we have many different types of fuels, a gaseous fuel like your propane, your methane, your cooking gas. Then we have liquid fuels like gasoline. Then solid fuels like wood, plastics, all of those types of solid fuels, coal, coke that we use as well. But what's actually burning, and it is the gas. So if we look at this candle, the candle blows out and we see the gas coming off. Look, the fire actually lit not from the solid wick here, but from up above. Now, as we can see that in slow motion, we can see the gases, which are mostly carbon monoxide, CO, floating around the wick after it's been blown out. And then once the match is brought close to the gases, you can see the fire starts with the gas near the match and comes down to the wick. So it's actually the gases that are burning, and the flame is being caused by the gases being generated right here around the wick as the fuel goes into gas form. And then, as you can see, there's actually solids in the flame by the soot particles that will gather on the spoon here. So there's still solids within this as it burns. We talked about the need of oxygen. So as you can see, wood, kind of our natural fuels that we have there, this is burning very cleanly. because it has enough air. It's burning slowly, cleanly. It has enough air to support the combustion. If you look at the polystyrene, it's not. There's a lot of carbon bonds requiring a lot more air. So it doesn't have enough air to burn, and you see this soot. And what this soot is fuel. We have more fuel coming off that this smoke up here and soot could ignite and add to our fire load. Here's a very fuel-rich flame. Doesn't have enough oxygen in this torch, but when we add the proper amount of oxygen, you can see we have a very good flame, very high temperature. You know, you need oxygen in order for a fuel to develop heat. If you don't have oxygen, there will be no heat developed without it. As we decompose our solid fuels due to heat, we can see the fuels off-gassing through these pictures. And eventually the fire just keeps growing and growing the more and more fuel that we produce. So this sofa here is producing a lot of fuel that you can see off-gassing up and then adding to the amount of fire at the top of the room where it's very, you know, where there's more heat in that area. So here's an example of how the fire develops. And we'll just watch through this and see kind of the differences on where the fuel packages are. When you're in the corner, and when we talk about how heat transfers with fire dynamics, when your fuel's in the corner, it will actually grow a little faster because the temperatures will rise up quicker. Now see how it kind of dies down? And we'll just continue to let this go through.
Oh, hiyo ndio
You can see the fire grows up and it mushrooms out when it fills up the room. So it's all that fuel, all of that smoke is just now spreading across the ceiling and forward out. And as it keeps up, it keeps banking down. And we talk about the smoke level and how low the smoke is. The lower the smoke is, the more fire that there's been consumed, more material that's been consumed. So the more smoke we have, that's more fuel. If we get air, we can get a very large fire event once it gets enough air in that fuel. As you can see up, you can start to see some flame actually in the upper parts of the smoke. It's getting enough oxygen within the smoke that it's actually starting to ignite. We can see it continues to bank down. As that fuel package is generating more and more smoke, it doesn't have enough oxygen to free burn. And as soon as we would get enough oxygen into there, we have a very large fire event. Now we can see from the east view that it's totally blackened down. Zero visibility conditions means there's a lot of smoke, and behind that smoke we can see there's still fire burning, but there's still not enough oxygen to burn everything off. This would be a very dangerous situation for a firefighter to crawl into. There's hazards of zero visibility, but with that much smoke, there's also the hazard of a large fire event like a flashover occurring. And then at that point, flashovers, even with the best turnout gear today, flashovers are not survivable just because it instantly everything heats to ignition temperatures. The one interesting thing, you can see how it starts to, as the fuel burns off, we're basically getting the fuel's going down to a point where there is enough oxygen for it to burn better, burn a little more freely. And you can see how the flames aren't producing quite as much smoke. So speaking of smoke, basically smoke is just the solid and liquid particulate coming off of any fuel that's not burned. You know, is the unburned fuel, is that products of pyrolysis and combustion that when we heat up any material, it's off-gassing, giving off soot. If there's not enough oxygen, it's not going to burn off. It's just going to develop and carry off into the atmosphere. And if we contain that in a room, we basically charge the room with gaseous fuel. And as we talked about before, gas fuels are the only ones that truly burn. We have to take any solid and liquid and turn it into a gas before it will burn. So what do we get when we burn? Our products of combustion usually are carbon dioxide, carbon monoxide, soot, which is carbon particles and other solid particles, and then other hydrocarbons. So mostly when we're burning our plastics, we're going to get a lot of soot compared to other types of fuels. You know, polystyrene and polypropylene will produce the most soot of any of these other fuels. We look at like methane, which is our cooking gas. It's a very clean fuel. We have no, if it's set up properly, no CO, no soot, no other hydrocarbons, it will all convert into carbon dioxide. As we go through the more complexity in the chemistry of a fuel, like in the polystyrene and the polypropylenes, it's not as easy to burn and it requires more oxygen, resulting in having higher CO, having higher soot conditions for those fuels. So as you can see, a lot of the fires we're fighting today are involving those types of plastics, which are going to give heavy, black, sooty, oily smoke. That is another fuel, and once it gets enough oxygen, the smoke's going to burn. And that can put us in a very bad situation if we're not cooling that smoke. You know, when I first started out in the fire service, we were always told, don't put water on smoke. Today, it's actually changed that we want to put water on smoke. We want to cool that smoke when we're in a confined area, when we're in rooms that are very smoky. We want to cool that smoke to prevent it from igniting once it sees the air from, you know, that we have let in as firefighters. Apart from breaking glass and cutting holes, the most natural thing we do fighting fires will add air to the fire, and that's going in the door. For us to get to the fire, we have to open a door to come in. And as soon as we do that, we will start having oxygen and air go to the fire, and it'll increase the amount of fire present then. Oops, I want to go back on that, sorry. So if you can kind of look at the smoke off of these two things, This is just a stack of wood. Good, nice flame, not a whole lot of smoke. But if we look at these chairs, which are made out of synthetic materials, there's a lot of heavy black smoke involved. There's not enough oxygen where the fire is to be able to totally burn the gaseous fuels that are being produced from the solid materials here. So all of this is fuel that's in the gaseous form that as soon as we get enough air, we will have combustion into the smoke. Now the heat release rates, why is this important? This is really looking at how the fire is going to spread a lot of it. And it has to do with how the chemical properties of the fuel, how the fuel is physically in a room. Is it in the middle of the room? Is it in the corner of a room? How it's ventilated, how the room's ventilated. All of this stuff goes into the heat release rate. As we talked before, the faster the heat release rate, often the quicker we will use the oxygen and have the fire go vent limited and darken down to the point that we don't think there's a fire. And then as soon as we'd open a door, all of a sudden, whoosh, the air comes in, lights off the fuel that's there, because the heat's there, the fuel's there. All we need is that oxygen to be able to give it that self-sustaining reaction. The thermal conditions in a room, are very important. Something may be burning in one corner, and if it's producing enough heat, it can make something burn in another corner. Given the amount of heat that's released, given how it's releasing that heat and how it's carrying over that heat transfer into different areas of the room. And how much energy the other fuel within the room would require to actually ignite and burn as well. So these are just some things that the heat release of different types of fuels that we may have. A sofa can give off quite a lot of energy. 3 to 5 megawatts of energy just off of a sofa for a very brief period of time. So that gives you an idea of how much energy we have stored in our houses every day. Think of the chairs that you have, the sofas that you have, everything made out of different plastics. There's a lot of energy stored in our house just with our furnishings. And when something catches on fire, all of that energy is going to be released. And how that energy is released will impact how we as firefighters are going to have to attack the fire. So if we look at just a regular coffee maker, we can go from, at this test that was done at just a little over 10 minutes, it had released 40 kilowatts of energy. That may not seem like a lot, but that's enough if it's being transferred to other things around it. That energy can heat other materials to the point where we get the pyrolysis and we get the off-gassing to allow that gaseous fuel to be able to ignite from other materials around it. So this is a test showing the heat release rate just of a standard chair. They started it with a burner on the side. So the energy is transferring from that flame on the left side of the chair. And as we can see over time, the heat release keeps going up, and it will increase. And there they took the burner away. Now the chair is just burning on its own. Notice how the heat release rate dropped down a little bit when they took away the burner, but now it's starting to creep back up. And now it's decaying down a little bit. But as you can see, we're getting a lot of energy just off of a chair. You know, something we may not think that can lend a lot to our fire load, but we can see, and now we've got a big pickup in how the heat release rate picked up. So we're getting more air flowing around it. More of the fuel has degraded into the gaseous state. The hotter it gets, the quicker it can. The hotter it gets, it's self-sustaining. The more heat it puts off, the more gaseous fuel it produces. So until, you know, right now at like 9 minutes, we have a spike of, you know, 700 kilowatts an hour just off of one little chair. Now think if you had an office complex, you know, you go into an office building to fight a fire, you have hundreds of these chairs in those offices. Look at all the energy that's stored there and how quickly the heat can be released. So here, this one is one of my favorites to watch. You know, we see you have what we call our legacy materials. So that's cotton, wool. So you have a cotton and wool sofa on the left versus a synthetic sofa on the right with the same time lapse on how quickly it burns. Look at the heat release rate that you have on the synthetic material. Look how quickly that released its energy. Now, even at this point on the, you know, legacy material on that cotton sofa, I could probably take just a small bucket of water, pour it on the fire, and I can still use the sofa. You know, it's not that damaged, where the sofa on the right that was synthetic, it's already totally destroyed. And it will take more than a bucket of water to put the fire out. You can see that the sofa on the left is heating up still. You can see all that smoke. You can see it off-gassing, even where there isn't flame. You can see a lot of off-gassing. And then all of a sudden you'll see this gas start to turn into flame as the sofa burns. But even at the end, you can see, went too far off. At the very end, when they stop the experiment, there's nothing left. This is a synthetic sofa, yet there is still, you can still tell this was a sofa. So there's a big difference in how quickly energy is released from synthetic materials versus our natural materials such as cotton, wood, wool, those types of things. And this is a chart off of that experiment. You had a peak with the synthetics. You know, there was a big spike in our heat release rate, where with the natural fibers, it just was a pretty much a steady release, and you saw kind of like that nice steady burn with it. So and this was, you know, you look at this chair, and the instructor that was giving our class, he picked this chair out because it was mostly synthetic, and to see, you know, what a common chair that most people are having in their houses today, how quickly things are going to be destroyed by fire, how quickly pyrolysis happens, and how quickly the fire can spread given the amount of heat that they're releasing. And you can see this is just a chair by itself. If this was in a room, it would be heating up the entire environment around it, which would probably be very similar material that would quickly burst into flames on its own once it got heated up and everything off gas. So that entire chair is pretty much reduced to nothing in less than 5 minutes. So we can see that we get a lot of fire growth, a lot of fire spread very rapidly with rapid heat release with our synthetic materials. Now the heat transfer and the energy transfer, this is what's important. This is kind of really important as far as how fire is going to spread. You know, there's 3 modes of heat transfer that we need to be aware of. And it's as that energy flows from area of high temperature to area of colder, lower temperatures, the lower temperatures will increase to the point that we'll get fire spread. So we're looking at conduction, convection, radiation. Conduction is when heat transfers between 2 things that are touching. Convection happens when air or fire gases are flowing over an object. They transfer heat that way. And radiation is just basically electromagnetic waves heating the surface. The best example of radiation is the sun. The energy and the heat we feel from the sun is in the form of radiation. So you can see for conduction, the temperature goes through from the front of this plate to the back of this plate. So the temperature is hot up here, it's cold back here. The heat flows from the hot side of the plate to the cold side of the plate. Copper, things we use for plumbing, copper, steel, those are what we call really good conductors. They will move heat very easily. This is important for us as firefighters to know, what makes up pipes, what makes up wires, copper, steel. Those metals will help move heat in a building that we may not see. So if you have a fire in one room and there's copper pipes in the walls that got heated, well, all that pipe could carry that heat to a different area and start a fire somewhere else based on the heat carried by those pipes. The other side is, brick, glass, those are what we call insulators, and they stop the flow of heat. So if we build a wall out of brick, that would be more of a fire stop. Fire's not going to be able to penetrate that, and it's not going to be able to go through. It's not going to transfer heat to actually catch things on the other side on fire as well. For us as firefighters, we're going to get heat transferred to us through conduction when we're crawling along the floor. So where we're touching the floor, we're going to get heat transferred to us through conduction. Also, we get heat transferred to us, to our bodies through our gear. When our gear presses on us, like where our BAs are, and anything else we have that will push our gear down towards us and touch us, that would be transferring heat to our bodies through conduction. For convection, as we see the fire gases and the smoke flowing over this plate, it's heating up by the airflow or the smoke flow over this plate. So you can see, even though there's nothing touching this probe and the flame, there's still air movement because hot air rises. So as that air rises, it's moving and heating this element here. We get convection as the smoke flows past us, we're getting heated by convection. As the cool air comes underneath us, the cool air comes in to feed the fire, we get cooled by convection. So we're getting heated and cooled by convection. And this isn't just us, this is also any victims we may have in the area. Radiation needs nothing to transfer the heat. It doesn't need contact, it doesn't need airflow. It can actually transfer heat through a vacuum, just like the sun transfers heat through the vacuum of space by radiation. So different materials will absorb energy from radiation differently. Most, like your polished steels, they reflect anything that's bright and shiny will reflect most of the energy by radiation. Things that are dull and dark colored, they're going to be absorbing most of the energy from radiation. This is how a lot of fire spreads between buildings often is radiation. We'll have one house that's on fire, and then the house next door, even though there's nothing connecting the two houses, will start to burn based on all the radiant heat transfer from one house to the other house. So as a firefighter, we're going to get bombarded with radiation when we go into a fire room and we see the fire, and we'll get all that radiant energy that our gear is absorbing. And usually a majority will get, when we're in the rooms, this is when you're inside the enclosures, most with the flowing smoke and the flowing air, most of the heat transfer will be convective. But when we're out in the open, most of it's going to be a lot of radiation as far as the heat transfer will be radiative. And we don't, not only do we get radiation from the actual fire and we get heat transfer from the fire, we get it from the smoke. So this is all high temperature smoke up above us. It's radiating heat down on us as well. And as things get hotter, and this also shows, like talking about pressure, as things get hotter, we have a temperature, the pressure increases. So that's why smoke pushes out of windows, smoke pushes out of doors, smoke will push out of any crack. Things are going from high pressure to low pressure. So as you get a bigger fire, it makes more pressure. You're going to see higher velocity smoke coming out. So as you look at it, what atmospheric pressure is 14.7 pounds. That's the normal pressure that we're all subjected to every day. So we don't notice that pressure, it's equal around us. And this is the pressure that we look at. You know, we look at pressure when we operate our fire apparatus. But the big thing with fire dynamics and pressure, the hotter the fire, the more pressure we're generating in the room, meaning that we're going to be pushing smoke and fire to areas of lower pressure. If we disrupt this pressure balance, like say we see fire pouring out of a window, we can put water in that window, but we have to do it correctly, not to upset that pressure balance. If we do it with a straight stream going in just the corner of the window and not covering up much of the opening, it's a very good tactic. If we set a very big fog stream pattern and we cover that window, well, the fog stream's making a higher pressure. That higher pressure is pushing the smoke and fire back in through the building. That's not what we want. We want the fire to vent out naturally and to go to those low pressure areas. We don't want to obstruct any of the ventilation holes. And then as we cool the fire, it will bring the pressure down. As we decrease the temperature, the pressure will decrease. So kind of a summary of what we talked about, to have fire, we need fuel, oxygen, heat, and self-sustaining chemical reaction. Natural fuels and synthetic fuels are very different as far as their heat release rate, the amount of oxygen they require, and the amount of how quickly they give off that energy. Big thing to take away, smoke is fuel. We want to keep that smoke below its ignition temperature. If we keep that cooler, we're going to have less of what we call large dynamic fire incidents. If we don't have oxygen, we're not generating heat. But without oxygen, there still will be heat producing fuel, but until we give it enough, until we give enough air and oxygen to that fuel, it won't have flaming combustion or fire. So that's why we need to control, how we ventilate and how we open doors, how we open windows, how we open up buildings that allows air in. The larger the heat release rate, the bigger the fire hazard. And we get higher heat release rates with our synthetic fuels. So more synthetic fuels, bigger fires. Everything's going to go from hot to cold. So if something's hot, it's going to make something that's cold. It'll eventually get hot due to the different things we've talked about as far as heat transfer. And all of our pressure as far as our smoke conditions and our airflow is going to flow from high pressure to low pressure. So that's, as you can think of, as something's burning, the temperature rises, the hot smoke is at a higher pressure up top, it's pushing out. As it pushes out, there's actually a lower pressure at the base of the flame, and that helps pull the oxygen in. So it's a kind of like an air pump that the fire becomes, because of heating the air, going up, lowering the pressure at the bottom, pulling air in. So that's this is kind of just the basic high level fire dynamics, how things behave. When we talk about advanced fire dynamics, we basically will take all of this information and plug it into how things happen in a building, and talk about flow paths, ventilation control, how the fire dynamics go into your tactics and strategies as far as fighting a fire. And there's a lot of other resources out there that you can use and are very easy and free to access. The Fire Research Institute is an organization that has produced actually this presentation and a bunch of research on it. So these are places where you can get more education online about these topics. They do a lot with like water mapping, air entrainment, and they also have programs that are good just for the community as well. One of the big ones they've done is the close before you doze, to make sure that when people go to sleep at night that they're closing their doors. This is actually, we have found it's very effective to, even with a raging fire outside a door, even the cheapest door that we can go buy at our hardware store will hold back fire long enough that it's potential to save, people from fires. But it all goes with closing doors before they go to sleep, and giving that fire, making a fire break, and something that minimizes fire spread. These are other organizations that have a lot of training available online. ISFSI, International Society of Fire Service Instructors, the CNET. And this is at Close Before You Doze. more public education. As you can see, a totally destroyed room on the left with a door closed, it kept the temperature survivable. So this limited the convective heat transfer for the gas flow. It minimized the radiative heat transfer from the fire since there was a door blocking it. So, just a simple door will do a lot to save lives in the fire. Then the Explorer Lab. This is really cool website that UL has put out there for education purposes to learn a lot of different things about, fire, also electrics, like battery powered stuff, how it could affect fire growth and things. So there is a lot of free information out there. So that wraps up everything I have. If there are any questions, I'm going to hang around and do my best to answer them.
Awesome. Thank you so much, Ed, for that. And thank you to everyone for coming and joining us today. That was a really amazing and informative training session that we just had. So thank you so much. I'm sure that there are some questions. And so as Ed said, that he'll stick around for tea time. If in the beginning of tea time, you want to take time and ask those questions, but we are just going to wrap up the training now. So thank you so much for everyone for joining. And as I said earlier, please always feel free to use the registration link that you guys joined through today to send that to anyone else that might be interested in the fire service and interested in these trainings. We're growing like crazy right now, and so it is just so fun to see that. And so I invite you guys just to always be doing that and always be sharing our networking group on Facebook or just any of our social medias as well. And with that, I'm going to be passing it off to our fire safety advocate, Jose, to start our training. So thank you, everybody. Bye-bye.